We're going to be using Einstein's famous equation, E equals mc squared, and we're going to be writing down some calculations step by step. So and we're going to try to go slowly through those calculations, and so you can see exactly how all the numbers work out. But be ready to take careful notes when we get to that. I'm going to start with with some comments about the exam. It's not graded yet. Hopefully we'll be able to hand back exam printouts on Tuesday next week, same as last time. Hopefully that'll be good for you guys. I was going to say something else, but I forget now. Something about the exam. Actually, here's something I'd like to mention to you. I haven't graded the clicking items yet either, so that's, probably gonna get all that stuff squared away this weekend. And I might have, the scantrons might be done, they might be done today. If they are, then I'll try to post some of that stuff over the weekend. In our grading scheme overall, after today's midterm after Tuesday's midterm is posted, most of you will have 2 exam scores. All right? Now we're shooting for 3. And we're going to keep the best 2 out of 3. But you'll have 2 scores. You may drop one of them after exam 4. Hopefully you do better on exam 4 than the first 2, and then we'll drop one of them. At any rate, you have 2 exam scores on the books now. So technically you can figure out your semester grade or estimate what it would be today or as soon as I post your exam scores. So we're at that point in the semester where now we can get serious because we have 2 exam scores. Also, we're going to be doing some clicking. Have your clickers ready. I'll try to post an update on the clicking participation the clicking participation scores. Okay, how many you've answered, how many of those that you've gotten correct. So it'll be, last time I posted it, it was for October 10th. And so I'll do a roundup today, so that'll make it October 26th. So that's roughly 2 weeks, that's not bad. So it'll be, last time it was so many answers out of 15, so many correct out of 15 questions. Now we're going to be up in the 20s somewhere. So that'll change. And I'll take down the earlier number. So that'll vanish from your grades page, but a new pair of lines will appear with the October 26th roundup. So that'll allow you to figure out your full semester grade. We're going to have some homework over the weekend, some reading, and probably a little mini quiz, some reading questions. And I'll have that ready for you by lunchtime tomorrow, if not sooner, due next Tuesday. It'll be on chapter 15 and 16. Now we're going to start with some comments here about chapter 15. And then we're going to dip forward into chapter 16. And then we're going to dip backwards into chapter 15 next week. So we're going to, chapter 15 and 16, just think of it as one big chapter. All right? And we're going to be zipping and zapping, different places today and Tuesday in those 2 chapters. All right? Anyway, questions about exam scores and stuff like that before we proceed further? Okay, let's keep going. Now, this is a comment, and this is a pull quote from chapter 15. The sun's core is extremely dense and is the source of all of its energy. Inside the core, nuclear energy is being released. And that one sentence is kind of a good summary of what we're going to be talking about today. The structure of the sun is pretty important, but to really understand what's happening, we're going to talk about the nuclear energy reaction that takes place at the core. So let me remind you that, for instance, this is HL Tauri. We're looking at a protostellar disk. The planets are clear in the nebula. And actually, that is a star, so it's not protostellar. That is a stellar disk. It's still pretty dirty. The planets are clearing it. The star HL Tauri is clearing it. That's a hot young star. How that star, what we're going to be talking today about is how the protostellar disk gravitationally organizes itself. And in the very center of it, where the star will be formed, you undergo gravitational compression and heating and start a nuclear reaction. And so the sun structure, as I said, is important. Here's a diagram from chapter 15 on the different layers of the SUN. And, you know, I was just reading an article from 2014 in the journal Science, and you'll have a reading, that'll be one of your additional readings for the weekend. This is what we would call a radial model. In other words, there's only one dimension that matters, how far you are from the center of the sun. Are you 2,000 kilometers up, or are you 200,000 kilometers up, or, you know, where exactly are you from the center? So make a note, this structure diagram here is a one-dimensional structure, the dimension being radial distance from the center. And so everything else is symmetric. We usually model the sun as being spherically symmetric, even though it's slightly unspherical, it's slightly squished. But what in my reading, the additional reading that you'll have, that I was actually looking through it last night, it was kind of cool because we now have this spacecraft called IRIS that allows us to see in the outer layer of the sun's atmosphere some three-dimensional structure. In other words, you know, basically all we have here is a one-dimensional model, but we can now see with some of our equipment the three-dimensional structure of things that are happening on the sun. So, oops, wrong direction. So the innermost part of the sun is its core, of course, and that's where the nuclear reactions are happening. It's a nuclear fusion reaction. It's hydrogen nuclei fusing into and changing into a helium nucleus. The outermost part of the sun structure is known as the corona. That's the part that you see during a total eclipse of the sun, you know, when the moon is up there obscuring. And in between the innermost and the outermost, there's a huge bunch of physics concepts that work. Now, you can read about them, but I'll just verbally mention a few. There's a lot of convection in the SUN because a lot of it can be modeled as a fluid where the density is changing and the temperature is changing. And because of those things, you get roiling and boiling, just like boiling water on the stove. You know, the hot water bubbles up, and the cooler water, it cools off a little bit and it dips down along the edges of the pot. All those structures, I keep blazing this thing up, sorry. All those different concepts. Another one is the radiation zone. That's in there as well. So the whole idea of radiation, electromagnetic radiation. Another one here is magnetic fields. There's intense magnetic fields in the sun. So make a note of that, magnetism, electromagnetism. It's not just gravity driven. There's enormous magnetic effects. The sun has a pretty strong magnetic field, and it actually has something that here on Earth we do not have. That is, it has really strong, fairly small-sized magnetic fields that are revealed, for instance, in sunspots and stuff. And you can see a few sunspots on this diagram. Sunspot is basically formed when there's big, powerful magnetic fields looping out from the surface of the sun and then back down to the surface on the other side. And we don't have those on Earth. We have a fairly mild, local magnetic field. So in other words, we can't go to a location on the planet Earth and have the compasses go haywire. You know, unless you're in a, unless you're in a building where the steel structure's been magnetized. But basically, the Earth itself never does that. So if you were to go to a mountain where there's a lot of magnetite, which is the form of iron that forms magnets, the lodestone principle, it wouldn't be as strong as the ones that we observe in the sun. So magnetism is pretty important. And we'll talk about more about these different layers probably on Tuesday. Before we do that, we have to talk about a basic concept that we've used, but now we have to get down to brass tacks, and that is energy. So this will be the second basic topic for today. What is energy? And we're actually going to be talking about luminosity as well. Energy in the metric system is measured in something called joules, also calories. But calories are a unit of energy in the unit system that are usually associated with heat processes. But the more general one is joules. And so, for instance, the 1 joule is the kinetic energy of a 2 kilogram object that it's moving at 1 meter per second. And here's the formula. If you had a physics class in high school, or maybe even middle school physical science class, you may have seen this formula, 1/2 mv squared, the mass of the object times the square of its speed. So whatever the speedometer rating is, and if you rate the speedometer rating in meters per second, and the mass in kilograms, and then multiply it all out, you'll get a number of joules. All right, and a joule is the most basic metric unit of energy. Okay. Side note. You could jot this down on the side of your. 1 meter per second is about 2.24 miles per hour. Let me repeat that so you can add it to your notes. Just something to think, because we're going to be working in meters per second stuff. But, the world we live in here in Orlando is miles per hour for a lot of things. So 1 meter per second in the metric system is about 2.24 miles per hour. So this object, 2 kilograms, so that's like a 2-liter bottle of Pepsi, because a liter is about a kilogram. So this is about a 2-liter bottle of Pepsi, traveling at about 2.24 miles per hour. That would be 1 joule of kinetic energy. So it's the metric unit. Now, luminosity, we usually rate that in watts. And that's in how many joules of energy per second are produced by the star in terms of sunlight, starlight, or anything else, X-rays and stuff like that. All right, so the watt is, so when you have when you pay your power bill, if you have an apartment, sometimes your power is paid in your rent stuff, but if you have to pay a separate power bill, it always comes in kilowatt hours. It's 1,000 watts times 1 hour. And that's an amount of energy that you're buying. But your basic objects like a light bulb is rated in watts. That tells you how many joules per second this thing uses to produce light. And for a regular incandescent light bulb, 60 watts, yeah, it's using 60 joules. It's using the kinetic energy of 60 2-liter bottles of Pepsi moving at 1 meter per, at 2.24 miles per hour. Right now the sun, here's the luminosity of the SUN. Write this one down carefully, because this is the one that we're going to be tackling today. Its luminosity is 3.8 times 10 to the 26 watts. My wonderful students, 10 to the 26 is a ginormous number, okay? And guess what? You can make a side note over here. The sun is no great shakes as a star. I mean, it's nice. We like it and everything. But there's much bigger, brighter stars, and there's a lot tinier stars too. You know, like Alpha Centauri C, which is right now the closest member of the Alpha Centauri group. It's a small red star. It's pretty modest. So the sun's brighter than Alpha Centauri C, but you know, like Betelgeuse or Polaris, they're way brighter than this. Anyway, sun is pretty bodacious. And so make sure you jot that down. And one other thing I want to recall to your mind is the solar constant. We talked about this a couple weeks ago. This is the amount of radiant energy from the SUN per square meter that's facing the sun. Now, at our distance from the sun, the amount of joules per square meters is about 1,367. And it varies slightly, you know, depending on, so it's not really a constant. It depends on who's measuring it and how you're measuring it. But 1,367 is pretty good, all right? But in Mars, on the surface of Mars, it's quite a bit smaller because Mars is further away. So every square meter of Mars facing the sun, directly to, you know, pointing directly at the sun, catches less than 1,367, and Venus and Mercury catch more than 1,367. So it just depends on where you are in the solar system. Now we're going to take both of those numbers, make sure you have that one down too. We're going to try to make sense of them. Now I want to give you a couple more examples of kinetic energy. For instance, a Bumblebee Camaro, I wish I had one, can do the quarter mile, 115 miles per hour in 12 seconds. So, and that is actually 2.2 million joules. I mean, you work it all out. And I looked up the specs for it. They did some road tests. And that's, you know, Detroit does that all the time. And they publish, you know, for something like a Ford Fiesta, they're not really going to make a big deal about their road tests. They'll test it, you know, on the quarter mile, 0 to 60, and all that stuff, but it's not built for speed. But this one is, man, pretty nice rig. Anyways, 2.2 million joules, or 2.2 megajoules. So capital M stands for mega. All right. Now you can see I've got a tank down here. The M1A1 Abrams, pretty nice piece of equipment. They fire, you know, a bunch of different kinds of rounds, but one of the rounds is about 12 megajoules. And oh my goodness, those things can get up to 50 miles an hour, probably more. You know, the guys working, you know, the mechanics and the drivers and stuff, they probably soup them up as much as they can. You know, take off all the governors and stuff so they can get it up to as high as they can get. I don't even want to think about the kinetic energy of that baby. I mean, Camaro going 115 miles an hour versus an M1A1 Abrams going 50 miles an hour. Oh my goodness, that's a lot of kinetic energy. I'll have to figure that out one of these days. Anyways, a good tank round is 12 megajoules. Navy's railgun, estimated at 32 megajoules. I'm sure they don't want everybody to know exactly what it is. hypervelocity projectile. But 32 megajoules is what is commonly conceded the energy range for that railgun projectile. Anybody here, here in Florida, I don't know how many people will do this, but raise your hand if you have a hunting rifle or any kind of firearm and you do your own reloading of your ammo. Anybody? Okay, a couple guys. And out in Montana, half the class should be raising their hands, you know, because out there everybody hunts and stuff. Everybody's got guns and rifles and whatnot. Anyways, if you look at, a lot of times, you look at a box of ammo, or if you're reloading your own stuff, one of the things that you consider is the kinetic energy of your round, you know, of your bullet. And that's related to, you know, the stopping power for that particular bullet. So that's another one you might see occasionally. Now, I want to develop the power rating for the Camaro. We know it's 2.2 megajoules, and we know that it develops that in a space of 12 seconds. So let's just take the average power rating here. 2.2 megajoules divided by 12 seconds. So type in 2.2 in your calculator and then hit the EE button and then the 6, that's 2.2 million, and then divide by 12 and you get 176,000. All right, so that would be 176 kilowatts for a Bumblebee on the quarter mile. Now, let's compare that to a hairdryer, and you can go out to Walmart or Kmart or anywhere else and buy a hairdryer that's rated at 1750 watts. Okay, that's 1.75 kilowatts, so that's a little bit less energy. And you may say to yourself, Dr. B, how come a hairdryer is rated at 1% roughly of Bumblebee Camaro? Bumblebee Camaro is definitely more than 100 times more bodacious than a hairdryer. And the answer to that is hairdryers use up a lot of energy and a lot of power because they're wasteful. All the heat that is poured out of the hairdryer, you know, to dry your hair is waste heat, and it's very, very inefficient. So, you know, the fan is fairly efficient, but the heating elements in there. So like a toaster, you know, a toaster doesn't even have a fan, but a toaster is going to use a lot of watts to do a fairly small task. So it's kind of a luxury, I guess. Another thing, well, let me pause for questions. Kinetic energy in joules and watts. Whose video is that? Who's playing? I can hear your music. Pelsman, Mr. Pelsman, are you here? Just checking. All right. Okay. Let's go to the next topic. This is like a subtopic. We have a very specific temperature scale that we use in physics for most things. Now the Weather Channel, those guys are scientists. A lot of them are physics types, but they're talking Fahrenheit and Celsius. Astrophysics and most every other type of physics talks about Kelvin scale. It's also known as the absolute scale. It uses Celsius-sized degrees, but the 0 point is not the freezing point of water. So this diagram over here tells the three. So let's take a look at this thing. It's got Fahrenheit on the left, Celsius in the middle, and then the Kelvin scale on the right. Now, boiling point of water and freezing point of water are over there on the Fahrenheit scale. So let me get my cursor over here. All right, so here's freezing point, 32 degrees Fahrenheit. Everybody knows about that. And then 0 Fahrenheit is down here. And 212 Fahrenheit's up here, that's the boiling point. So Fahrenheit, notice that there's 180 degrees between those two temperatures. Just like there's 180 degrees turning halfway around a circle. That is not a coincidence. Fahrenheit, Professor von Fahrenheit, back in the, I don't know, 1700s or whatever it was, designed it that way. Now the metric scale, Celsius, that's here in the middle, and with all metric scales, they wanted 10, 100, 1,000. So they went with 100. And so boiling point of water is defined to be 100 Celsius. Freezing point of water here is 0 Celsius. And the 0 point of Fahrenheit, now look at this, the 0 point of Fahrenheit is a negative number for Celsius. So, you know, where you define the 0 point is up to you. You have freedom as to where you put the 0 point, and you also have freedom as to how big the degrees are. Okay, so there's 180 degrees of separation between freezing and boiling water on the Fahrenheit scale, and there's 100 degrees between freezing and boiling water on the Celsius scale. Mental IQ test question. I should have put a clicker question for this. Which scale has larger degrees, Fahrenheit or Celsius? What do you think? Fahrenheit has larger degrees? No, yes? I don't know, I'm sorry. It's all right, I'm just trying to see what you're thinking. So you say Fahrenheit. Why do you say that?
No, I was wrong because it's a bigger gap, and then I was like, no, that makes sense.
In the back.
I think Celsius because it takes less degrees to get to the same point. So.
Good. Do you agree with that?
Yes.
Okay. So it only takes 100 degrees to go from freezing to boiling for Celsius, but in Fahrenheit, there's more of them, but they're smaller, right? So now, the Kelvin scale, we've got a different 0 point. It's not related to water, okay? For Fahrenheit, that scale is related to the thermal behavior of water. Celsius, thermal behavior of water, boiling and freezing. The Kelvin scale is actually defined differently, so that the 0 point down here is actually the absolute zero of molecular motion. So quantum mechanically, we know that things are still kind of oscillating down there at 0 Kelvin the fanciest way to say it is that you cannot run a heat engine and extract work from something at absolute zero. It's the lowest possible temperature, and below that, our definition of temperature stops at 0 Kelvin. All right, so that's absolute zero. Now the thing about it is, on the Fahrenheit scale, that's negative 459 Fahrenheit. Right, so the 0 of Celsius was a positive 32. The 0 of Fahrenheit was a negative 18 Celsius. Now the 0 of the Kelvin scale is negatives for both of them, negative 459 Fahrenheit and negative 273 Celsius. So if you ever have a Celsius temperature, now the other thing about Kelvin scale, it's the same size degrees as Celsius. So make a note of that. Same size degrees, and it's absolute zeros down there. So that's where we put the 0 point, and then we just build Celsius size degrees up to that. So the freezing point of water in the Celsius scale is 273. Our temperature is about 300, our body temperature. Okay, 290 something, right in there. Round it off to, no, room temperature, about the same. So, and you know, you can work it out. I hate converting from Celsius to Fahrenheit, but, and you're not going to have to worry about converting from Celsius to Fahrenheit. But I do want you to remember Celsius to Kelvin, it's plus or minus 273. All right? To go from Celsius to Kelvin, you add 273. To go from Kelvin to Celsius, you subtract 273. So it's pretty nice that way. Instead of like going from Fahrenheit to Celsius, you know, you got to add 32 or subtract it and multiply by 5/9 or 9/5 and all that rigmarole. It's a pain in the so we're not going to do any of that. But yeah, the Kelvin scale is what we're going to use. Now, the reason that we need that is because the Kelvin scale is a physical scale. It's an absolute scale, and it is the thermodynamic scale that we use to rate the heat content of a physical process, its absolute temperature, okay? And the temperature of the surface of the sun, for instance, is 5,800 Kelvin, so, which we'll be talking about. So we'll talk about the Kelvin temperatures of stars for the rest of the semester. Next topic is electromagnetic radiation. Very basic topic, and I want to go over with you. And it is the principle of Roy G. Biv. Now, there's his yearbook picture from 1982. This is kind of a goofy-looking guy, Roy G. Biv. And he's famous. He comes from a family of famous physicists, all named Roy G. Biv. And they're famous because their name, did you write it down in your notes? Roy G. Biv, famous scientist. His name and all of his great-great-grandcestors is the exact order of colors in the visible spectrum. Red, orange, yellow, green, blue, indigo, and violet. All right, so just remember, when I refer to Roy G. Biv, I'm talking about visible light. Okay? If I mention visible light, you can think, oh, okay, so that's red, orange, yellow, green, blue, indigo, violet. Now, you may have perfect pitch color-wise, visually, but I do not know the difference between blue and indigo. Anybody in here an art major? Do you art majors, do you know the difference between blue and indigo? Seriously? Good. I'll have to learn something. I'll have to study up on it. I've been dealt with. I thought nobody knew the difference, but I guess some people are smarter than me on colors. That's all right. Anyways, so Roy G. Biv, it's what do you call it? An acronym for the colors. Now, let's take a look at the sun's atmosphere. This is from the SOHO satellite. You can look at pictures of it every day. This is a false color UV image. So it's actually taken in ultraviolet at the specific wavelength. Go ahead and write down that wavelength. 304 angstroms. 304 angstroms. An angstrom is a 10 billionth of a meter. It's very small. So 304 of those is pretty small. The electromagnetic radiation at that wavelength. So you know you can look in your diffraction grating and make a picture of the sun with your diffraction grating set to 304 angstroms, and that'll be your so that's how you measure the ultraviolet, and it corresponds to plasma in the atmosphere of the sun at about 60,000 Kelvin to 80,000 Kelvin. Now this is a false color image, so they made it kind of orangey and white and black where it's not very hot at this wavelength. And here's just a little blurb. An angstrom is 10 billionth of a meter. 1 times 10 to the minus 10 meters. All right, now, here's another picture from the SOHO satellite website. And I can't remember what the day is on this one, but you can look up this image. This is 171 angstrom, false color ultraviolet, slightly smaller wavelength, and corresponding to plasma, whoa, 1 million Kelvin. Holy buckets. We're really burning here. All right, so 171 angstroms, 1 million Kelvin, and this is part of the atmosphere of the SUN. Now, notice that's not the corona, or not much of it. That's just like the base of the corona. Now, you got to get a little bit hotter, and here's the next one. It's false color ultraviolet, 195 angstroms. Okay, now this one we figure this one's at plasma of about 1.5 million Kelvin, 195 angstroms. So slightly different wavelength. And notice that this one, it extends a little bit further than the previous one, the false color blue. All right, so 1.5 million Kelvin. So we use ultraviolet, and we use Roy G. Biv as well, and we use infrared to tell the approximate temperature of an object. So let me repeat that because it's pretty doggone important. We use the dominant color or wavelength of an object to numerically measure its temperature, its surface temperature. All right? And so this is dynamically measuring everywhere in the neighborhood of the sun's atmosphere where we've got plasma at about 1.5 million Kelvin. Now here's an even bigger spread. Now this one's starting to look like the corona. 284 angstroms, and this corresponds to plasma at about 2 million Kelvin, and it's a lot bigger. In fact, it went off the charts over there on the left side. Okay, so this is another false color ultraviolet. And you can do similar images in infrared. You know, sun is, you know, nice. So this is the atmosphere. Look at this big gap here, right here in northwest quadrant. And you know what? It doesn't look very good on the... Can you cut the lights up here in the front? Very good. Yeah, that's a little bit better. It'll look really nice in the YouTube. Those are what we would call a coronal hole. Right? And those are important to know about. We want to know all about those bad boys. Here's another black and white at 67, 68 angstroms, kind of reddish. And this one's optimized to show the polarity of the magnetic fields on the sun. All right, so the whites and the blacks are places where the magnetic field is either north or south. You know, like you take a bar magnet, it's got an N and an S end, and then you know, if you want, you can use it as a little compass and stuff, and it'll swing towards the Santa's workshop or away from Santa's workshop. So we can actually analyze electromagnetic radiation and figure out the polarity of these different sunspots. So you can see that every sunspot here, like over here and down over here on the far right edge, they've got a black adjacent to a white, and that means that there's a magnetic field looping up into space and coming back down, like a bar magnet that's been turned into a U-shape, or a horseshoe magnet. All right, a horseshoe magnet might have a black and a white color like that as well. So that's what we think is happening in the sun. Now we're just taking a preliminary look at this stuff. I'm relating color and temperature for you with these last few pictures. Now I want to talk more about gravity and fusion. Get your clicker out. I have a couple of questions for you concerning Roy G. Biv and stuff. And we're going to talk about how the fusion reactions start in the center of the SUN. And we've got about half an hour, 30 minutes for this, so let's work carefully. Here's your first question. What happens to your hands when you press them together and go like this? "30 seconds to vote. "10 seconds. Or 20 seconds, I should say. "10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. One person voted for B. Okay, you know, I can figure out who it is too. Anyways, the correct answer is A. A couple people voted for C, and actually that's not correct. When you rub your hands together, they're not going to get red hot. If you rub them together until they did get red hot, then they'd be emitting a little bit of Roy G. Biv. They'd be emitting some R. Okay? But I don't think anybody can get their hands that hot. So theoretically, they're emitting just a teeny bit of Roy G. Biv, but mainly they just warm up. Okay? So pressing stuff together is a way to warm things up. Now, next question. Student with last name Pelzer, P-E-L-Z-E. Are you here right now? Raise your hand if you're here. We want to double check something. All right. Which object heats up more from gravitational compression? Did you correct the first one? Okay, thank you. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Come on, you guys, get your answer in. Think. Make a decision. Sitting on the fence? Okay. No dineros for you. Click. All right, and go ahead and show this one, please. We got some splaining to do on this one. And this is fine. Go ahead and switch back to regular. The answer is the large mass. And you know what the example is for this? So if you answer the larger mass, the example of this is Jupiter versus Saturn. Remember we talked about that? The pillows effect? If you have more pillows, it might not look bigger, but it's going to compress more. And that's the same thing here. So the objects in a protostellar disk that have larger mass are going to compress more. And because they're compressing, they're going to heat up more. And if they heat up enough, they'll be able to start a thermonuclear reaction. So let's take a look at this. All right, so this is what happens to form a star or a planet that we saw, for instance, with HL Tauri. And heating is significant. But it's not enough to provide the luminosity of the sun. So no matter how much gravitational heating, we worked this out in the 1800s. They figured out, well, maybe it's just putting out all that energy because of gravitational compression, heating things up, and so they glow, like a red hot furnace or something like that. But they worked out the numbers and they said, it can't be that. It's got to be something else. And the reason for that is gravity is pretty weak. It's the weakest of all the four forces of nature, but it's infinite range, and it cannot be screened because it's always attractive. So it dominates in astronomical distance scales, but it's still pretty weak. So compared to the two nuclear forces, it's really, really weak. And compared to the electromagnetic force, electromagnetism, for instance, it's also very weak. So, so what we understand now is that the only thing that can be happening is some kind of nuclear reaction in the sun. And because we know that the sun is mostly hydrogen and helium, we've decided that it must be some kind of a hydrogen fusion. In other words, it's not uranium fission. It's not splitting uranium atoms and getting excess energy. It's fusing hydrogen atoms or hydrogen nuclei into helium nuclei to get excess energy and therefore heat. Now, the equation that governs all of this is Einstein's most famous equation. You can read more about it in, this is now chapter 16 concepts. E equals mc squared. And it's one of the most famous equations in history. It's right up there with the Pythagorean theorem and stuff. I bet more people know this than just about any other equation except for maybe the Pythagorean theorem. I mean, think about it. What equations can you think of that everybody, I mean, you may know a few, equations F equals ma from Newton's second law of motion, but not everybody's going to know that. Only if you've had a physics class. You may know the equation for converting Celsius to Fahrenheit, but I definitely know not everybody's going to know that because I happen to deliberately not remember that. But this is one that I think enormous numbers of people have heard about. And what we're going to do now is learn what it means. So let's talk about how much hydrogen the sun burns in fusion reactions per second. What happens is when, and you can make a note of this and you can read about it in chapter 16 over the weekend. When hydrogen nuclei fuse and form eventually a helium nucleus, the mass of the helium nucleus is slightly less than the mass of the hydrogen nuclei that formed it. There's 2 neutrons and 2 protons, and in the reaction, 4 hydrogen protons fuse and become 2 neutrons and 2 protons, and the mass of those 4 together are slightly less. So there's some missing mass for every time there's a fusion reaction, and that missing mass goes into energy. And that's what we get here at Earth's surface, 1,367 watts per square meter, basically from the nuclear reactions in the core of the sun. Okay, so just to repeat how this works, think of an imaginary sphere of radius 1 astronomical unit. All right, and so what that does, if you convert an astronomical unit into meters, and then use the formula for the surface area of a sphere, 4 pi r squared, and then multiply that by 1,367 watts per square meter, you'll have a number of watts. There it is, 3.85 times 10 to the 26. So our Earth only catches a small fraction of that sphere. All right, and we get 13, we have a lot of square meters, but the square meters of the entire sphere of radius 1 AU is ginormous. But it leads us to this conclusion. We measure every square meter out here at 1 astronomical unit catches 1,367 watts. Nice. The entire sphere. So if you have this imaginary sphere around the sun, solar cells everywhere on that sphere catching every ounce of energy. This is how much energy, basically how much power you could catch from the sun. 3.85 times 10 to the 26 watts, 3.85 times 10 to the 26 joules per second. And so that's the approximate luminosity of the SUN, right? Now, using E equals mc squared gets us to this number. This is the amount of mass. This is the change in mass of all those fusion reactions. Remember, I told you, every time the hydrogen nuclei fuse together and form a helium nucleus, there's a little bit of missing mass, delta M. Okay, the difference in the mass before and after. And so every second, we figure that the sun is converting this much mass into pure energy using E equals mc squared. All right, and so go ahead and jot that down, 4.28 times 10 to the 9 kilograms per second. Now, that's my mass per second. Now, if I multiply that by c squared, it should come out to 3.85 times 10 to the 26 joules per second. All right, so let's do that. All right, so E equals mc squared. So per second, we're going to put in that last figure in the m there, and then we're going to multiply by c. Now, c squared, c is 3 times 10 to the 8 meter per second. So the square of that is 9 times 10 to the 16 meters squared per second squared. Okay? So jot that down carefully somewhere to the side. All right? And so we measure the solar constant. We figured out, you know, for every square meter at 1 astronomical unit, we figure out that we've got to have 3.85 times 10 to the 26 watts. All right, now here we go. That is going to be equal to some amount of energy, delta mc squared, per second. So that's what we're trying to figure out here. Right? Now, so make a note here, 3.85 times 10 to the 26. That is a measurement, that is a calculation based on our measurement of the solar constant. Let me repeat that for you. That number, the luminosity of the sun, is a calculation based on our measurement of the solar constant. You know, we can measure it here on Earth, you know, up on top of a mountain. We can measure it from satellites and stuff, the space station, everything. So we can get a fairly good estimate of the solar constant and then do the surface of a sphere, 1 astronomical unit radius, and we come up with 3.85 times 10 to the 26 watts. All right, now Einstein says, all right, guys, it's not gravitational compression, it's E equals mc squared. So I'm getting that much energy per second out of some m and some c squared. Now, c squared is a constant of nature. But the m is the missing mass, so delta m here, that's the missing mass of all the fusion reactions. Right? So those fusion reactions, the reason that they're so powerful is they convert just a teeny fraction of mass in every hydrogen to helium reaction into energy. That mass goes somewhere and it goes into energy. All right? That's what we're trying to figure out here. All right, so divide both sides by c squared, okay, and you get this down here, 3.85 times 10 to the 26 watts, that's the total luminosity of the sun. Divide that by c squared, and you'll get delta m. Yeah. And so now let's put in the number for c squared. And it's going to look kind of bodacious, but it's not that bad. 9 times 10 to the 16 in the denominator. Keep the numerator the same. Now, notice that I converted into, this is a joule here. I'm just looking, I should have made this a little different. This says watts here, but I should have joules because I'm implicitly doing this for 1 second. So this down here, kilogram meters squared per second squared, that's a joule. That's like 1/2 mv squared. A kilogram times a v squared, meter squared per second squared. And then down here, this is c squared, meter squared per second. And if you look at this quotient, you'll see that meters squared per second squared cancel. And you're left with kilograms, all right? So that's pretty nice. And then all you have to do is divide 3.85 by 9. And then you got 10 to the 26 over here and 10 to the 16. So that's going to simplify to 10 to the 10th power on top, right? And that's right here. So 0.428 times 10 to the 10 kilogram per second. Now I've got my per second back in there, all right? So that's a huge number of kilograms per second. All right, so there's your calculation. Now let me pause for questions before we continue. Yeah.
So that's the kilograms per second without the
Yeah, so in E equals mc squared, this is the m that goes through E equals mc squared every second of the sun's existence at the current luminosity. So, you know, it was probably a little bit not as bright earlier in its life, and it'll change its luminosity, you know, gradually, but right now it's pretty stable. It'll be this for many billions of years, we think. Another question? Yes? No, we're calculating it now so that you know the numbers where I got them. Yeah, you won't have to do this, unless you want to. Because I know some of you guys finished awfully fast on Tuesday. So I was up there thinking, man, maybe I should make the test harder for exam 4. So I could, now what is your name again?
Sarah.
Sarah what? So Sarah wants a harder test, I guess. I could, okay, I'm just kidding around. No, this kind of thing, if we were in, you know, like physics 2048 or 2049, maybe we'd do a calculation like this. Or have you taken any astronomy above 2002?
Yeah.
Like
Planetary geophysics.
so if you're taking planetary geophysics, you might do this. You know, but for us guys, no. But we're doing it nice and slow so that you know where the numbers are that you're gonna. Here's the number that I want you to think of. 4.28 times 10 to the 9 kilograms per second. That's what I want you to think with. And so now you know where that number comes from. But here's the kicker. The sun's got 2 times 10 to the 30 kilograms, right? And you're only dipping out 10 to the 9 kilograms per second. So the sun is barely notices that. And so you can ask yourself, well, all right, how much of the sun? It's a lot to us, 10 to the 9 kilograms, that's a billion. That's 1 million metric tons, 4.28 million metric tons. So that'd be a big chunk of Earth every second, converted from hydrogen into helium with the excess energy, with that amount of mass being converted into pure energy that ends up as sunlight. So you may say to yourself, well, how long can the sun keep doing that? Well, let's figure that out. Okay, so let's figure out the fraction of the sun's mass per second. Right? So let's look at that rate. Right? All right, so we figured out from E equals MC squared, Sarah, that we're going to get 4.28 billion kilograms every second, roughly. All right? So that's Einstein's equation, equals MC squared. That's the numerator. And how do we know that? We know that because we know the solar constant. And we can do a little bit of math. All right? So we know the numerator there. Now the total mass of the sun is about 2 times 10 to the 30 kilogram. So the fraction of the sun lost per second is this rate. So this is a fractional rate. So let's work it out. All right, so let me park this down here. Let's work it out. All right. 10 to the 9 on top, 10 to the 30 on the bottom. So the numerator is going to have 10 to the what power? 10 to the 21st. Positive or negative? Negative. Right. All right. And then the numeric part is going to be, oh, this one's easy. 4.28 divided by 2. That's 2.14. That's easy. So that's the mass of that's the fraction of the sun's mass that it loses per second. So if it was losing 2% of its mass per second, that would be 2.14 times 10 to the minus 2. That would be a percent. Right? But this is 10 to the minus 21. So we're talking a very, very, it's not per mil, it's not per million, it's not parts per billion, it's parts per 10 to the 21, which is ginormous. All right, so this burn rate, 4.28 times 10 to the 9, in 1 year, okay, go ahead and jot this down. In 1 year, 31,536,000 seconds, the sun converts 1.35 times 10 to the 17 kilograms. So multiply that number here, the kilogram rate, times 31,536,000 seconds, and that tells you how many kilograms in a year. Okay, it's 1.3, you can do it if you want on your calculator. There it is, it's 1.35 times 10 to the 17 kilograms of its mass per year into energy. How many years can that go on? Let's figure that out. Right? So now what we'll do is we'll put the total mass of the sun in the numerator, 2 times 10 to the 30 kilograms, and then we'll divide by the rate that it loses mass per year. Okay, we already know per second. This is per year now. Okay, so 4.28 times 10 to the 9 per second, 1.35 times 10 to the 17 per year. Now, let me point out something to you. Question in the back? Stretch it. Good. Let me ask you a mental IQ test question. You're traveling (100 miles) at 30 miles per hour. How much time would that take? How would you figure out the time? What divided by what? 100 miles, 30 miles an hour. So you're driving in the granny lane. What do you think? No, I don't want to know the answer. I want to know how to calculate it.
Oh, you take 100 miles that you're driving, divide that by the 30 miles per hour that you're driving.
Okay, you take the total distance divided by the speed. Okay, and that'll give you 3 hours and 20 minutes. 3.33 hours. Okay, so now this is not a distance and speed calculation. It's a mass and mass loss equation. So what we have here is like 100 miles in the numerator and 30 miles an hour in the denominator. Okay, so for our problem, we put the total mass of the sun up on top, and the rate per year that it loses mass. This will tell us, 100 miles divided by the speed tells us how long it takes you. Total mass of the sun by how much it loses per year will tell you how many years it'll take. Right? So, all right, so hey, you guys, what's the power of 10? It's going to be, this quotient is going to be 10 to the what power? 13, right? Because you got 10 to the 30, 10 to the 17 in the denominator. And then 2 divided by 1.35, that's going to be like 1 point something, okay? Can somebody do that, 2 divided by 1.35? Who's got it? What do you got? 1.48, or about 1.5 times 10 to the 13 years. My wonderful students, I want to tell you that the age of the universe is something like 10 to the 10 years, all right, approximately. So this is longer than the age of the universe. So the sun, if it keeps burning hydrogen at the rate that we've measured, using E equals mc squared as the energy production rule, which is what we're using, is going to keep cooking for a long, 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 long time. It's not going to run out tomorrow, the next day, the next century, the next million years, or the next billion years. It's going to, what is that? 10 to the 9. That's going to be, 10 to the 4 is 10,000. So 10,000 billion years. 15,000 billion years is how long that'll go. So the sun's got plenty of energy. It's cooking just a small fraction of its mass, and it's burning real bright and nice, Lewis. Okay, plenty of light. Small amount. So we got a good stable star here. All right. Now, things will change eventually, because when you start accumulating a lot of hydrogen in the core, a lot of helium in the core will start to collapse, and then you'll start nuking off different reactions. But this one will be stable for quite a while. We think the sun is going to be cooking at this rate for billions of years to come, we think. Unless we get, nuked by another star plowing into the sun or something like that. But Bruce Willis will come out of retirement and save us. Maybe even Arnold will have to be dead, or Chuck Norris. Anyway, so the sun is very stable, and it kind of tells you that these nuclear reactions are extremely powerful. Diffusion equals mc squared is extremely powerful. A little bit of matter, and when we have these atomic reactors, they're not really converting a whole lot of mass into energy. They still have a lot of uranium left. It's not like it disappears in a poof of smoke. These nuclear weapons, they detonate them and there's this big mushroom cloud and everything. But they don't, they're only a very small fraction of the mass is converted into energy. It still is, enormously explosive. And this is even more bodacious. So this serves as an introduction now to a lot of the numbers that we're going to use to think about, Sarah, when we're studying our star, the sun. Let me pause for questions here. Anything here you want me to review? Or you have a question about? All right. Let's dismiss early. There will be a big reading assignment, as I mentioned, homework 8. It'll be due Tuesday. Be ready to work on lunchtime tomorrow, maybe sooner. You're dismissed. I'll see you next week.